Welcome to day 2 of the advent of compiler optimizations. Today we're going to look at addition, just adding integers together. Over here in Compiler Explorer I have a very simple function that just takes an x and a y, both integers, adds them together and returns them. The x86 ABI on Linux, which is what I'm using here, says that the first parameter goes in RDI, the second parameter goes in RSI, or EDI and ESI, and then the result should go in EAX. We talked a little bit about that yesterday. So what does the compiler do? You might think that it would use an add instruction. There is an add instruction in x86, but as you can see, it doesn't. It uses this LEA instruction. Again, if you've stared at any assembler in Compiler Explorer, you'll have seen LEA a dozen times, but it's an incredibly versatile instruction, and we're not even really using it for what it's supposed to be used for. So what is LEA? LEA is load effective address. It uses the x86's rather complicated addressing modes, but instead of accessing the memory at the operand, that is this complicated thing we'll talk about in a sec, it just says, well, what would be the address of that memory were I to actually access it. So it's a little bit like C's address of ampersand operator. x86's memory operands are complicated. You get a base plus an offset and a constant. The base and the offset can be registers, and then one of the offset registers can be multiplied by 1, 2, 4, or 8. So it's kind of a convenient way of accessing an element in an array of shorts or ints or longs or chars, right? Why is this important? Well, the address unit that has to generate the address to read and write from is quite complicated. It has this adder and this potential multiplier that multiplies by 1, 2, 4, or 8. The compiler knows this, and it uses the LEA instruction because it's a convenient way of adding two numbers together and getting the result. Why doesn't it just use an add? It would seem to make more sense, right? Well, unfortunately, the x86's ISA is a little weird. Most instructions only have two operands. That is, they have a source and a destination, but the sort of destination is also one of the sources. So most of the instructions like add are more like a plus equals operation. So it's like EAX plus equals RDI. That's cool, but it does have some side effects. It means that we lose one of the two sources of our add. It's replaced with the result of the add, which is sometimes inconvenient. But moreover, it means that we can't control where the result goes. It has to be one of the two input values. That's where the result of the add goes. So if you imagine what the compiler would have to do if it used an add instruction, it would have to add RDI and RSI. Now the result would be in RDI or RSI, depending on which way round it added the two numbers. Then it would have to move the result into the EAX register in order to get the result into the return value. So that would take two instructions. In fact, if we turn the optimizer down to 0, as well as seeing it do all sorts of awkward things with manipulating on the stack, we can see that it does use an add here. But by this point, it's already stored and restored the registers from the stack. It can read the results out into EAX and EDX and then add them together and get everything in the right place. But that's not very convenient. So the compiler is pretty aggressive about generating the LEA instruction even at low optimization settings because it's convenient. It can put the result of the add into the destination register all in one instruction. One thing you'll notice is that the two operands on the right hand side, RDI and RSI here, are the R version. That is the 64-bit version of the register. Why is that? We've asked it to add integers, which are, in this case are 32 bits. Well, because it's designed for addressing, those values on the right hand side are always 64 bits because it's a 64-bit address space. That doesn't matter in this case because the ABI guarantees that the top 32 bits are 0, and having added them together, we discard the results by writing to EAX. So we can use the destination can be a 32-bit register, but the operands on the right-hand side have to be 64-bit. That's it for today. We've talked about how adds are optimized by the compiler, and tomorrow we'll look at some other strange cases. And later on, we'll also look at how other architectures deal with adding and subtracting and multiplying and that kind of stuff. So it's not just going to be x86. I hope to see you tomorrow.